Papa Flammy's Advent Calendar.
Good morning, fellow mathematicians. Welcome back to another video. Video sponsored by Extra Wallets. More information at the end of the video. They are producing some very nice lifestyle products. Also, don't forget to check out Stemmerch, 10% of all Cursed Math Memes, Newton's Abominations t-shirts. Okay, that's the counterpart to this absolutely highly orgasmic t-shirt design, and also 10 to 15% of everything over on my Teespring shop using code 426.9 checkout. So today we're going to do some more physics here on this channel, and I'm kind of excited about it because we are going to do rotational mechanics today. And what we're going to do is going to lead to Kepler's problem, which is going to deserve its own video. It's pretty cool. And today we are going to talk about the angular momentum as the rotational counterpart to the regular classical mechanical potential. No, not potential, momentum, I'm very sorry. Then also the torque, conservation of momentum, and at the very end, conservation of energy and rotational systems and effective potential. We are going to derive it today. It's a pretty cool thing. Maybe you have used it kind of before as a Coulomb potential in electrostatics. It's pretty cool. So we are going to talk about this today. Pretty excited. So at first, think back to regular classical mechanics and the regular momentum. It's being defined as being nothing but, so the vector is mass times velocity. Okay, this is what the regular momentum looks like. And we have kind of this momentum also in rotational systems. Imagine we have some kind of satellite, okay, approaching a planet, and due to the gravitational acceleration or attraction, it's going to hit the planet at some point, okay? It's going to spiral down to the planet. This is one scenario you could have, okay? Just we are going to have something like this. And then we have a mass going in this direction, for example, okay? And always as a tangent to this circular path is our velocity, or in our case, since our particle has some mass m, it's not only the velocity, it's a momentum in some way. So we have a momentum in this direction, but we also have a radius vector going down exactly to the center right here, to the planet. Now, they are both enclosing an angle, be it 90 degrees or not, okay? They probably won't have a 90 degrees angle being enclosed by each other, okay? This radius vector and this momentum vector. But for example, a situation where we have a 90 degrees angle is a nice circular path, okay? We have a mass m here, has a velocity in this direction, meaning since it has a certain mass, it also has a momentum in this direction, and we have a radius vector going right down here to the middle, okay? Those enclose a 90 degrees angle, and you can always express relationships between vectors and angles using the cross product. And this is like the main motivation behind the angular momentum, namely the angular momentum being defined as capital L with a vector on top is being defined as the r vector and the cross product with the momentum. Now the momentum by definition is nothing but m times velocity, but velocity is nothing but the r dot vector basically, okay? So we have m times the r vector and the cross product with the velocity r dot vector. Yeah, and those are the prerequisites, and with this useful thing right here, with this little formula, we can derive a whole lot of stuff, and with a few simple argumentations. And at first I would like to differentiate this thing right here, okay? Just the angular momentum. So what about ddt of the angular momentum? This thing in physics is called the torque. We're going to denote the torque with this n vector. Okay, maybe it has a different name too, capital M, or like, I know, I really don't care what you call it. In German it's called the Drehmoment, okay? And we are using the n. And now we are just going to simply differentiate what we are having here, okay? Or we can just differentiate that, okay? Really doesn't matter. We are going to differentiate the r vector and the cross product with the p vector. Now, the cross product is nothing but a multiplication of vectors, you could say. So formally, the product rule also applies here. Meaning the product rule states that this right here is ddt of the r vector and the cross product with the p vector, and added to it just the r vector and the cross product with differential of the p vector. Now, if we differentiate a momentum, okay, this is nothing but the mass times the velocity. Velocity differentiate with respect to time is an acceleration. Acceleration times mass, that's a force. Okay, so this thing right here is nothing but a certain force being applied. But what about this part right here? Let us write this out a tiny little bit more. I mean, we have m times our velocity, we can bring the m to the front, okay, it's just a scalar and we can drag it out of this whole vector that we are going to get out on the other side. So we have mass times, okay, ddt of r is nothing but the velocity in the cross product with, and what's left? That's just the velocity. Okay, now here's a little bit of prerequisite. If we have a vector a, and then in the cross product with the vector b, this is going to result in the absolute value of a times the absolute value of b multiplied with the sine of the angle enclosed by a and b. Now what about the vector in the cross product with a vector? Oh, I mean, if we have two vectors which are the same, they are basically parallel. Parallel means they enclose an angle of 0 degrees or the counterpart is 180 degrees. Never mind the situation, sine of 0 or 180 degrees is going to be nothing but 0. Meaning this whole cross product is going to vanish, it's going to die in hell somewhere, meaning our torque can be expressed as nothing but, well, the r vector in the cross product with a certain force, or if we were to rewrite it, this is mass times the r vector in the cross product with the r double dot vector. And now you can also have conservative laws, meaning when is our angular momentum being conserved? In physical terms, conservation means that our angular momentum, for example, is constant, meaning if we were to differentiate it with respect to time, then we are going to get 0 out. Meaning our angular momentum is going to be preserved if the torque is exactly 0. Just as a little matter of fact, and this happens by this rule exactly when our force and our r vector are parallel to each other. Meaning, for example, on a nice circular path, we are going to have the situation that our force is going to be either if you have this Scheinkraft, the centrifugal force, it's going to point to the outside, okay, and it compensates on a circular path with the force going to the inside, basically. This is the centripetal force. And yeah, this is the situation that you can have. And there you have the conservation of angular momentum. This is just something I wanted to talk about. And now we have derived a bunch of stuff. And we want to take a closer look at this relationship right here, because we can actually work with this cross product a tiny little bit more. And for this, I would like to take a look at a certain situation that is pretty close to this situation that we're having here, for example, with this closed path. Right here. Let's imagine we have, for example, a planet going around another planet in a nice elliptical curve. I don't care, okay? Kepler's law, we are going to talk about this later. Meaning, it's going to move basically in a plane, okay, around this other planet. Okay, if we don't talk about curved space-time and all this shit, it's just moving in a plane around it or not spherical geometry. Or another situation is you can have a marble, for example, on the table. This is a Lagrangian thing we're going to talk about soon, and it's just going to rotate around the origin, and maybe it can converge to the origin. This is also something that can hold. Never mind the situation, we are going to imagine it as being a mass, okay, rotating on a plane in some way. Meaning we have a certain velocity going this way, or instead of a velocity, we have a certain momentum, and also we have an r vector pointing right to the origin of a coordinate system. Let's say the origin of the coordinate system is right on the table, meaning this table that we have in this situation is going to turn out to be just the xy plane, for example. Meaning if we were to draw a coordinate system into here, we are going to get something like this. We have an x-axis, a y-axis, and a z-axis. And now we are going to write the cross product out that we're having here. Now, what about the L vector? How is it going to look exactly? Now, the L vector is going to be comprised of an x-coordinate, a y-coordinate, and a z-coordinate, obviously. But it's also defined as being a cross product, meaning this right here is the cross product of those two vectors, Rx, Ry, and Rz, and the cross product with Px, Py, and Pz. Now calculating the cross product is rather easy. It's just a bunch of permutations and differences going on in the entries. Now we are going to multiply those two together, leaving us with Ry, Py, pz, negative, and now just the indices changed, meaning p and rz. Next up is this and that multiplied together, so rz px minus rx pz, and at the end all the other entries that are not yet taken, namely we are going to have rx py minus ry px. Now we are going to take a look at the right-hand rule, because the right-hand rule can be used to actually visualize how the cross product and its outcoming vector is going to behave in the system. Namely, our thumb is going to be represented by the first thing in the cross product, namely the r vector. Our other finger that we're having here, okay, is going to point into the direction of the second thing in the cross product, namely P. And this thing right here, okay, taking Papa Flammy out of context yet again, the middle finger is going to represent the outcoming vector, namely our angular momentum. Now in this situation, how it's going to look? I mean, our r vector is going to point into the middle of our coordinate system, meaning our angular momentum in this situation is going to point towards the blackboard, meaning our angular momentum is going to point in the upwards z direction. Meaning it really doesn't have any x and y component, it's only comprised of a z component here in this system. Meaning this part and this part is going to cancel out. Those are just going to end up being 0, leaving us with a z component of the angular momentum, and two vectors are exactly equal if and only if the dimensions and also entries are equal. Meaning this difference is 0, this difference is also 0, leaving us only with the angular momentum in one dimension basically, namely a z component. Lz is hence nothing but r times x, rx times py minus ry px. But also don't forget what p is, it's just mass times the r dot component, meaning we have a certain mass, okay, as a common factor, and then we are going to have rx times r dot y minus ry times r dot x. And this is our boy, the angular momentum in this system. And now we are going to just multiply stuff together. We are going to find out what the r vector is, what it's comprised of. It's in the xy plane basically. Then we are going to multiply it together with its velocity counterparts, and then we are going to take difference and see what we are going to get. So at first we are going to take a look at the plane. Now, how is our particle moving? In our situation it has a certain radius, okay, here's our mass m, and also it has on the x and y axis an angle phi that is being enclosed and changing over time. Also our radius r can change over time if we have this certain situation where a planet converges towards another planet. So this right here is the rx component and it's the ry component. And now we can just make use of simple trigonometry basically, namely rx over r is nothing but cosine of phi, meaning overall if we were to solve for the rx component, rx is hence nothing but the cosine of phi times r, and also the same should be with the ry component where this is just the sine of phi times r. Okay, polar coordinates, we have talked about this extensively before. Now meaning our r vector is being comprised of those two entries, which is r times the cosine of phi and then r times the sine of phi. Now this right here is the first part, but for our momentum to pop out here, we also need to differentiate our rx and ry components respectively and then multiply everything together. Meaning if we were to differentiate all of this, r dot is going to be r dot x and r dot y. And now, remember what I just said? The radius can change over time, just like in this situation. It can get smaller or bigger, really depends. But also our phi is with respect to t. It's also time dependent because, well, it's going to move in circuits, so it's bound to move between 0 and 2 pi in some way. Meaning, we have to use, when differentiating both entries, the product rule at first, but on this part we also need to use the chain rule because this is cosine of phi of t, meaning this is going to turn in negative the sine times the inner derivative with respect to t, which is phi dot. Meaning overall, like I said, polar coordinates, analytical mechanics playlist down there, this is going to turn into r dot times the cosine of phi. This is the first part of the product rule, and then negative. Okay, r is going to be a constant for the second part. Then we are going to get phi dot times the sine of phi. And down here we have the same situation, just with a few signs flipped. And that's it. Now we can start multiplying stuff together, and don't forget your little m that we are having here. Meaning Lz is going to be m times. And now we are going to take a look at this part multiplied with those, and then after that subtracting this part multiplied with those. Let's go ahead and get started. So I'm going to make this bracket a bit bigger and write everything underneath each other because it's a bit easier to see. So we are going to get, okay, this is going to result in r cosine, so r dot cosine of phi times the sine of phi. And the second part is, okay, this is going to be r squared phi dot cosine squared of phi. Next up, we are going to get r dot, and don't forget, we have a negative sign going on here, so we have to subtract this next part from everything, times the cosine of phi times the sine of phi. And last but not least, in the normal case we would have negative, but negative and negative is going to become positive. Then we're going to get r squared phi dot times the sine squared of phi. Okay, so we have m times this chunk. Now you might notice something curious, namely that's the beauty of polar coordinates and analytical mechanics. Those have different signs cancelling out. Also, those two factors are equal, meaning what we can factor out is cosine squared and sine squared. Cosine squared plus sine squared, trigonometric Pythagoras. This is going to turn into 1. Meaning overall, our angular momentum in this situation that we have bestowed upon us, okay, that we have incarnated, is nothing but m times r squared times phi dot. Meaning we can also find out what the angular frequency of the system is, namely phi dot is hence nothing but the z coordinate of the angular momentum divided by m r squared. And this right here is going to be mighty useful when taking a look at the simple conservation of energy in classical mechanical systems without any kind of friction. Namely, we have talked about this before. So this right here is already something that you might be familiar with. Okay, this right here is just the angular momentum being expressed using just the angular velocity being expressed with respect to the angular momentum. Now the next part is something that not too many people know. If you've never done formal analytical mechanics, then you might have never heard of this before. It's going to result in the effective potential. We know in classical mechanical systems we have that the total energy is nothing but the kinetic plus the potential energy. And the kinetic energy is always just mass over 2 times just the scalar product of the entries of our r dot vector squared. Okay, this right here is just a scalar product, meaning what we are going to do is we are going to multiply all those entries with each other. Okay, so this right here is just the rx component squared and add the ry component squared to it plus our u. And this is what we are going to compute now. I'm going to put it here, okay, just as a little side note, what all of this is going to result in. And once again, I'm going to write everything underneath each other. So if we were to square those entries, that's going to turn into a mass. That's going to give us r dot squared cosine squared. And then negative 2 times r dot, just a binomial theorem, phi dot. Can you see everything? I do hope so. And then we are also going to get the sine times the cosine, and then we are going to add r squared phi dot squared sine squared to it. This has been the first part. Now for the second part, just squaring everything yet again. This is going to turn into r dot squared sine squared, then plus 2r dot phi dot sine cosine plus r squared phi dot squared cosine squared. And now you might guess yet again, beauty of analytical mechanics. This is going to cancel out, this is going to cancel out. We can factor out r dot squared here, leaving us with cosine and sine squared, respectively added together is 1. So this is going to result in r dot squared. And then we are going to have the same situation here. Cosine and sine squared is going to be factored out from this part, leaving us with plus r squared phi dot squared. Ain't that cool? That's really cool, right? Meaning the total energy, even in a rotating system, is nothing but m over 2 r dot squared plus m over 2 r squared phi dot squared, and then plus some potential energy u, which is also dependent on the radius vector, you could say. And now here comes the good thing in. I mean, m over 2 times r dot is a velocity squared is going to be a kinetic energy yet again. So we have a kinetic plus a potential energy, but what the hell is this right here? It's also some kind of energy. I mean, we can only add energies together to get a total energy out yet again. Now what about substituting phi dot? Okay, if we have phi dot squared, this is going to result in Lz squared over m squared r to the 4th power, leaving us with m over 2. And then r squared and then Lz squared divided by m squared r to the 4th power. I mean, m and m is going to cancel out down here, r squared, and this is going to turn into a 2, leaving us overall with E being nothing but t plus u of r, and then plus, and now something strange, Lz squared divided by 2mr squared. And this thing right here is called the effective potential, okay? It's not, no. That wasn't accurate. The effective potential is the whole potential energy in the whole system of a rotational system. Okay, meaning the effective potential is being defined as this part right here. We have some kind of centrifugal term, you could say. It's a centrifugal energy. It's kind of weird, a centrifugal potential added to the regular potential of the system. Meaning the total energy in a system is nothing but T plus the effective potential, where our effective potential is nothing but u of r plus the angular momentum in the z component squared divided by 2mr squared. And this basically completes the overview of the effective potential. There was a long derivation, but it's pretty cool if you ask me. I really love it. We are going to use it in Kepler's problem, and I'm already pretty excited solving Kepler's problem, because this was one of the most fun parts in analytical mechanics for me ever, because it involved basically heavy integral transformations, which I find to be really cool. But before we actually end the video, don't forget to check out today's sponsor. Where is my wallet? I'm pretty certain that they gave me the wallet. The cat has it. I think the cat has it. Where's my wallet? Oh, I bet the cat has abducted it again. Hannah, where's my wallet? Acting like you don't know anything, huh? Seems like I have to use it. Ha! Found ya. You have stolen my wallet, huh? The app told me so. Yeah, there it is. Always stealing my wallet. Not gonna buy you any food? Yeah, now you're looking guilty. Oh, can't believe Anton stole my wallet again. He's always buying himself food from my money. I have to restrain him. It's really annoying. Like I mentioned before, thanks to Extra for sponsoring this episode here on this channel with their very cool looking wallets. I for myself got the aluminum ones. They are their newest collection and they look pretty good. This right here is the redwood version, and I love reddish colors, and this is pretty perfect for me if you ask me. And if I were to compare it to the Rich, you can't really compare it, because they are an own class for themselves. They offer you a new experience when it comes to wallets, because as you might have noticed a few seconds ago, you can track your wallet using an app on your mobile phone, meaning it's a smart wallet. You can also track it using your voice, using Google Home, etc., which is really cool. And how does it exactly work? Well, you get yourself this tracker card right here. You can also purchase the tracker card. This right here is a solar powered one, meaning the battery can never run out. You can put it on the back side of your wallet, and this way it won't take any space away from your actual cards that you can put in here. And then you can track it, okay? Just use your app and it's going to make wee wee wee, and you are going to find it immediately, which is pretty cool if you ask me. So meaning, you can push the cards out here. This wallet is not only easy to use, it's also impossible to lose, which I find to be really cool. You can actually get 25% of your whole order currently during their Christmas sale, so definitely make sure to check their website out. You can find a link down there at the top of the description. And this basically concludes the video. Thanks for watching. If you did enjoy this classical mechanics video, which I find to be really cool, very nice derivation, then make sure to subscribe to the channel as well as to share the videos around. Advent calendar, okay, it's a good time for me. I love creating videos for the Advent calendar, so if you got time for that, maybe share the video around. That would be really cool and support the channel by a big margin. Other than that, thank you guys for watching. Seeing you tomorrow on the next Advent calendar day, and ciao.